right, so I wanted to go over the Taylor theorem slash Lagrange error bound one more time to make it more clear. Okay, so the Taylor theorem says that if f of x has derivatives of all orders in n, or in an open interval I containing a, then for each positive integer n and for each x in I, we get this expression where we go all the way down to the nth term, and then we have this remainder. So where r of n sub of x is equal to the n, basically the n plus 1th term with this z in there instead of an x. And z is some value in between a and x. So Taylor's theorem comes from the idea that if we were to send n to infinity, then a Taylor series, or sorry, a Taylor polynomial would become a Taylor series. And a Taylor series is an accurate representation of f of x. So this is also a series. At least according to what we learned when we were talking about the power series and how they relate to the Taylor series. So thus, the Taylor polynomial, or poly for short, which chops off the tail of the series, is an approximation. So it's not exact. Therefore, there must be some remainder, right? Some remainder, which gives the error between f of x and the Taylor polynomial it represents. So Taylor poly that it represents. And so therefore, by Taylor's theorem, we have that there's this remainder, r sub n of x, and that's equal to the difference between f of x and the Taylor polynomial that we use. Now, this part's super important. So note that r of x is merely the n plus 1th term of the Taylor series. But there's a difference, right? So the difference is there's some z between a and x, and that z is some value between the center and the x value that maximizes the error. So that maximizes the error. But we don't actually know what z is. So z maximizes the error. It gives us the largest error possible, but we don't really know what it is, right? So that's kind of like the problem. That's the trick to this whole thing. And because we don't know what it is, actually, Taylor didn't really suggest a way to determine the value of z. But luckily in 1797, almost a century later, Lagrange, a famous mathematician, and Cauchy, who you've probably seen that name on other calculus textbooks, developed a way to quantify the remainder more analytically. Hence, we have the Lagrange error bound. So the Lagrange error bound. So essentially, Taylor's theorem and the Lagrange error bound are kind of the same thing. You'll find some sources will refer to this only as being the Taylor theorem, and this only as being the Lagrange error bound, but they're saying pretty much the same thing. The difference between Taylor's theorem and the Lagrange error bound is that there's some kind of an analytical way of actually calculating what this max is going to be. And in both of these forms of the equation, they mean the exact same thing. And it's important to note that m is the maximum of the absolute value of the n plus 1th derivative at z. So those are the same thing. So basically what you're doing when you're using these is you're trying to find the largest possible error. So you're trying to find the largest possible error. Okay, so tricks for finding z. So most of the time, we are dealing with either an increasing or decreasing function, at least within the interval that we're talking about. So this is going to be increasing or decreasing function, because our intervals are small. They're like between like 0 and 0.1, or 1 and 1.2 or something like that. So generally, not every single time, but generally we're dealing with either an increasing or decreasing function. And so therefore, if it's an increasing function, so we have something that goes like this. So therefore, let's say this is our a and this is our x. If it's an increasing function, then the greatest value on that interval is going to be at the x, right? If it's a decreasing function, let's say this is our x and this is our a, by the way, because sometimes one comes before the other. It doesn't matter which one comes first, and they don't always come in the same order. So in this case, my x would also be the largest, but it's the left-handed point versus the right-handed point, right? And so because of that, our z is usually either a or x, one of the two. So the easiest way to figure out which one it is you can plug a in and you can plug x in and see what gives you the larger value. So plug in a and x to see which gives you a larger value. And so therefore, the m, which is again the maximum value of the n plus 1th derivative at z, is going to either be f sub n plus 1 of a or f sub n plus 1 of x, not b, of x, right? So that's going to be your maximized value. You have to figure out which one it is. So that's oftentimes and usually kind of the situation that occurs. Other times, sometimes if you have sine or cosine, then you just want to take the absolute value and then you're going to let your m, which is the maximum of the n plus 1th derivative at z, you're going to make that 1. Okay, so now let's practice some problems. All right, so example 1 says use a 3rd degree Maclaurin polynomial. So that means our a is equal to 0 to estimate the square root of e. So that's e to the 1/2, which means our x is equal to 1/2. And then we want to find the maximum error. So we want a 3rd degree polynomial. We actually already know what e to the x is. And since we want a 3rd degree polynomial, that's going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. Now that's the 3rd degree polynomial, but in order to get to look at the remainder, or the error bound, we actually have to go out to the 4th derivative. But actually, let's go ahead and calculate this first. So if we calculated this according to our formula, we would have 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 cubed over 3 factorial. And that gave me, when I plugged that into my calculator, 1.6458. All right. So the question is, how good of an estimate is that of the square root of e? So like I said, we need to use the Taylor theorem or Lagrange error bound, where we have that r of 3 of x is going to be equal to the fourth derivative at z over 4 factorial times x to the fourth. So what's the fourth derivative at z? Well, so we had the series, but we actually have to, or the polynomial, but we actually have to find the fourth derivative. And so remember that every derivative of e to the x is e to the x. And so the fourth derivative is going to be e to the x. So then the question is e to the 0 or e to the 0.5 larger? Because we're in the interval for z. Our a is 0 and our x is a half. And so that's the interval we're in. So z is going to be either 0 or a half. And we actually have kind of a picture of the exponential function up here. And so you'll notice that it's an increasing function, and so we're going to want to take the right-handed point and use that. So when we plug that in, we get r sub 3 of 1/2. Actually, I'll do that in the next step. So just of x is equal to e to the larger of the two, so e to the 1/2 over 4 factorial times x to the fourth. So now we can go ahead and plug in our 0.5. So that's equal to e to the 0.5 over 4 factorial times 0.5 to the fourth. And when you plug that into your calculator, you should get 0.004. So this is our error. And this should be our maximum error, the largest error that we can get. So what does that mean exactly? So what that really means is that the value of the square root of e is going to be less than or equal to 1.6458 plus 0.004 and greater than or equal to 1.6458 minus 0.004, because that's what absolute value means, and I should have put this over that. There we go. So this is what that means. And so if I were to actually plug in into my calculator e to the 1/2, what did I get? I got e to the 1/2 in my calculator was 1.6487. So this was the calculator. This is the error. And this is what I found right here. And so if you look at it, it makes sense here. This is, I actually subtracted it in my calculator. I didn't write it down on the paper to see exactly what the difference was between these two, but it was definitely with less than 0.004. Okay. Hopefully that made some sense. Let's move on to the next example. So how many terms of the Taylor polynomial centered at x equals 0 are needed to estimate the cosine of pi over 6 with an error of less than 0.1234? So that's 4 zeros, so that's 10 to the negative fifth. I think it's easier to think about instead of having to count my zeros. Okay, so for this kind of a problem, right, we're using the cosine. So remember that the cosine is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial and so forth. Now we don't know how many terms we need to go out to, but we have at least an idea of what it looks like. Our remainder, r sub n of x, is going to be equal to f sub n plus 1 of z over n factorial times 6, or x to the n plus 1, right? Now, so the question is, what is this? So remember above, it says anytime there's cosine or sine, you want to go ahead and take the absolute value, because that the n plus 1th derivative at z is going to be either plus or minus the cosine of z, or it's going to be plus or minus the sine of z. Either way, if I take the absolute value of those, both of them are going to be less than or equal to 1. And so anytime you have sine or cosine, you want to use 1 as your m value. So you're going to use 1 here. Okay, so, and then the other thing we should talk about is that our z is in the interval from 0 to pi over 6. Okay, so now we can go ahead, since we're using the absolute value, we would say the absolute value, here, let me write it over here so I have enough space. The absolute value of r sub n of x then is going to be less than or equal to 1 over n plus 1 factorial times x to the n plus 1. So now I can go ahead and I can plug in my pi. And so I get, here we'll do it down here, Rn of pi over 6, I should say, is going to be less than or equal to 1 over n plus 1 factorial. And then I'm going to erase this 1 and put my pi over 6 to the n plus 1. So basically, that's our expression that we want to calculate, and we want that to be less than 0.12341. So what I showed you in class before is that you can actually go ahead and you can graph this. You can let this expression equal y1 and this equal y2, and then you can graph it. Another way that you can do it is you can literally just plug in n values. So let's just pick an n to start at. Let's start at n equals 4. So at n equals 4, that expression is pi over 6 to the 5th over 5 factorial. So when I put that into my calculator, I get 0.0003. Okay, so that's not enough zeros, so we need to go up. Let's go to n equals 6. I think is a good jump because we skip terms, right? So we don't actually have a 5th degree cosine or Taylor polynomial for cosine. So we should probably try n equals 6. And so when I plug in my 6, I get pi over 6 to the 7th over 7 factorial. And when I put that into my calculator, I get 0.123452. Yay! So that is definitely less than 0.12341. Wait, 1, 2, 3, yeah, okay. So, therefore, what we need is to go out. Actually, we wrote the right polynomial because we needed to go out to the 6th degree. So that's the perfect one. All right, and then on this last example, so there's 3 cases usually that kind of come up most often, and that is where you want to plug in your z by picking your z's from here, from the interval. Or you've got sine or cosine, so you want to let m equal 1. Or you're actually given the information that you need. So in this situation here, this statement right here tells you that this is your m, right? So it says a 3rd degree Taylor polynomial centered at x equals -3 is used to approximate f of -3.5. So if we know this, what is the maximum error? So again, we're doing r sub 3 of x, and that's equal to f sub 4 of z over 4 factorial times x plus 3 to the 4th. And it's x plus 3 because our center is at negative 3. And so now we can plug in r of 3 of negative 3.5. And then remember we said that the fourth derivative of f, well, you know what I mean, that one, is less than or equal to 48. So I can say that this is less than or equal to 48 over 4 factorial times negative 3.5 plus 3 to the 4th. And so all I have to do is plug in 48 over 24, which is really just 2, times negative 0.5 to the 4th. So when I put that into my calculator, I get 1/8. And so therefore, 1/8 is the maximum error that we would get. All right, so I hope that stuff made more sense. Good luck on making sense of the Lagrange error bound. Just so you guys know, from everything that I've read and researched and been looking into about this, this is considered by most the hardest topic in BC Calculus. So if you can wrap your head around this stuff, you'll be good. All right, good luck, you guys.